basically it's not good, right? So we go through your submissions and we found that you are not performing well, right? So, and yeah, we have like around so many zeros, right? And there are some people who copied from others as well. So the both the parties will get 0 marks, obviously, right? And the people who using WhatsApp or those applications while doing the assignments, they will have to face a Viva, and the late submission guys have to face the Viva as well, right? So, and so if you're not performing well on the assignments, obviously you have to struggle on the exam when you're writing the exam as well, right? So the best opportunity is to get some mark from the assignments, then score some marks from the exam as well, right? So you have, I think we have to conduct one more assignment, right? Then the assignments schedule is over, right? So, like this, if you consider this subject, so this is a kind of a practical course, right? So you have to do your own work, right? So you can't do any magic in the exam, obviously, right? Not on my question, obviously, right? So the paper, the style of the paper will differ from the previous years as well, right? So that's why we're asking you guys to do some work on the assignments, right? Get some mark from the assignments, right? So then, okay, that's about those things. The people who are copying from others, right? So if you keep doing that thing, so we have to take some actions as well, right? Okay, so today we're going to discuss about communication, some serial and parallel communication protocols, right? So, right. So this is our schedule for today, right? So first we discussing about data transmission, then the mode of transmissions, and some serial communication protocols, right? So what is meant by data transmission? So it basically means there are two or more parties, right? So they are transferring some data between those two parties, right? They basically transmitting the data, right? So in we are transmitting data in form of bits, right? So consider the methods of transmitting the data. We have two, serial and parallel transmission, right? So if you consider serial transmission, serial means obviously that is sequential, right? So so if it is sequential, we have to we have to, so this is, if this is if this is your data, right? So we have to put your data in kind of form of order, right? So if you're sequential, so one after the other, so the data will be transmitted, right? So then so the order is obviously important, right? So so that we can find this the transmission as a reliable the transmission method, right? So if you need to transmit this portion of data, right, to this receiver, right? So we have to, if it is serial, we have to send one after the other, right? So this is 0, 0, 1, 1. So we have to find a specific code. We have to put these data bits, right? So we have to put these bits and transmit to the receiver, right? So we have to follow a specific code, right? So that is the main part. Then if you can consider the serial transmission, so we are now discussing about serial transmission, right? Not about the parallel transmission. In the serial transmission, there are two. One is synchronous, then other one is asynchronous of this, right? So synchronous means we are syncing with some kind of, there are only two parties, right? Sender and the receiver, right? So in here we can T and other, right? Transmit and the receive. Synchronous means we have to sync with these two, right? So we can have several methods to do that, right? So asynchronous means there are no syncing. We just send in the data, right? Then the receiver receives the data. Okay. So in the synchronous transmission, to sync these two parties, transmitter and the receiver, so we are using kind of a clock, right? So this is the some shared clock. It's creating some pulses, right? So I'll right like this, right? So this is the clock, right? So this is the transmitter and the receiver, right? So this is the data we want to send, right? So we have some portion of data here, right? So this clock just creating some pulses in kind of a form of suppose 10 hertz or something, right? So it just creating the pulses, right? So these pulses sync in the transmitter and the receiver, right? So transmitter also, okay, by sharing this clock, transmitter also know that, okay, I should work on this kind of frequency. If it is 10, so I should work on 10 hertz, right? So the receiver also agree with that frequency. Okay, I'm also working on 10 hertz, like that. It's sharing with the transmitter and the receiver, right? Then, so each pulses, so these are the pulses, right? So the clock pulses. So this is the data line, right? So we have some portion of a data, right? So at each pulse middle, right? So this uh, receiver taking the inputs, right? So if it is right, so this is the, if you consider this one, right? 0, okay. So I'm looking at the data link. Okay, now it's high, right? So we have two, it's only two, it states. so this is high line. So we can consider as 1, and this is the low. You can consider as 0, right? So this data is sent in by the transmitter, right? Then the receiver should take those inputs, right? So how he going to like take the input based on the clock cycles, right? Clock pulses, right? So at each edge over the middle, right? So it's for the first edge, it's looking at the data link. So then take the data. Okay, now at this point, it's 1, right? Then again at this point, it's again 1. This point, it's now 0, right? So the data is looking like this, right? So we should take the inputs at each clock pulses, right? So I'll do some example, then it will be okay. Like as I said before, these clock frequencies shared with both the parties, right? So most of the time, this clock signal is generated by the receiving party, right? So the receiving party sharing this clock to the transmitting party, right? Right? It's like taking the inputs, right? Then there is a special group of bytes we call as sync signals, right? So that basically alert the receiver if there is a data is coming, then sharing the synchronizing the two devices, and after the transmission end, it's telling that, okay, I'm done sending the data, right? So these these so, these sync signals, like it's kind of a voltage pattern, right? So in this stage we have only these are the voltage, 0 voltage, high voltage, and the low voltage, right? So you have only the voltage, right? So there are no kind of a thing called bit or something like that. So we have the voltages, right? So these voltages in the very lower level, so these voltages creating these bit patterns, right? So there are some voltage patterns based on that. They're creating the those signals, right? Then right. So the one advantage is we can move our data very fast, right? So this because transfer and the receiver is syncing, right? So the timing error is also less, right? So but the thing is, if this depend if there is a error on the clock's pulses, right? So basically our data is highly depend on the uh, clock syncing, that shared clock, right? So if it is not syncing at that stage, so our data will be uh, received by the receiver, not as we expected, right? Then yeah, so in this example, right, so you can see, hope you guys hear me right now. Can you guys hear me?
Yes.
Okay, right. So there are two data lines, two channels, right? So one is a data line, the other one is a clock line, right? So this clock line basically supplied by the receiver, right? In the data line by the transmitter, yes, no, right? So this is pulsing at a kind of a predefined hertz level, right? Suppose 10 or 100, right? So it's pulsing at that level. Then, so this transmitter sending some kind of a data, right? So start from the beginning, right? so so if it is red means 1, right? So if it is white, that means 0, right? So this is pulsing at kind of a predefined level, defined frequency level, right? So at each pulses, if it is this place getting red at that point, it's the receiver looking at the data line, right? Looking at the data line, looking at this data line and take the inputs, right? Now see, now this is red at that point, so it should take the whatever the data in the data line, right? So now it is again red. So these are zeros, right? So if we start again, right, you can see if it is red, so it's the receiver come to the data line and check whether what is the data. Okay, it's red, that means 1, right? Then again, the clock line is red. Again, the data line also red, that means 1, right? Now, again, the data line is red, but the clock line is red, but the data line is white, that means 0, right? Like that, keep getting the data, right? So that is the basic theory behind this thing, right? So it has a clock line that basically sync in the transmitter and the receiver, right? So the both parties agree with that frequency level, and transmitter just sending the data, right? At each clock pulses, it's looking at the data line and take that input into the this its buffer, whatever, right? So is it talk? Is it clear? Hello. Any questions on this? Okay, someone asking to explain it like that. So, okay, go very beginning, right? So basically, we have two data transmission methods, right? So one is serial, other one is the parallel, right? So now in serial communication, we have again two types. One is synchronous, the other one is asynchronous, right? In the synchronous, give me 1 second. Right? In the synchronous means transmitter and the receiver is synchronizing, right? So that means it's it's sharing some kind of a common thing and sync with that, right? So like you dubbing something, right? So there is some kind of a voice and you dubbing with your video, something like that, right? It should sync, right? So if it is not sync, it's horrible, not right? Right in here, in synchronous, obviously transmit if there are two parties, so we are transmitting data, so there should be a data line, right? Then because this is synchronous serial transmission, there should be a clock, right? Shared clock between these two parties, right? So this is, we call it data line, and this is clock line, right? Then, so this is the example, right? So this clock line, it has kind of a predefined frequency level, right? So it's keep creating the pulses, right? Like that, right? So it's not affecting anything, right? Then what's happening? So this signal most of the time provided by the transmitter, right? Then so this is the receiver, and this is the data line that's coming from the transmitter, right? So at each clock pulses, right? So if it is red, that means it's like blinking and not blinking, right? So if it is red, that means so at that point you should looking at the data line and take the input, right? Right. So if it is, so I'll start from the beginning, right? So now it's getting red. Okay, at that point, so receiver go to the data line and take the input and put it to the its buffer, right? So it's red now. The data line also red. That means it is one, right? Again, the next bit. Again, it's the data line is red, but so clock line is red, but the data line is not blinking. That means 0, right? And again, it's getting red. Data line also red. That means 1. Like that, at each clock pulses, so the receiver check the data line and takes the inputs, right? Okay, is it clear? Okay, right. Then the second one, so that is we discuss now the synchronous one. Okay, right. Now the asynchronous method, right? Asynchronous means there are no such synchronizing mechanism, right? We are just using some kind of stop bits and start bits, right? So we have kind of a portion of data to transmit, right? Then we are putting some start and stop bits to tell the receiver in. So if the receiver receive this start bit, so now the receiver know, okay, I should take the start to receive some data, right? So this is the actual data portion. After the receiver receive this stop bit, now the receiver know, okay, I'm done. So the transmitter done in the transmitter done the transmission, right? So the receiver know, okay, I should stop receiving the data, right? So basically it has stop bit and start bits, right? So, so this is the sender and the receiver, right? So we are putting kind of a, so this is the actual data portion, right? The two sides we are putting, so this is the receiver. So we are putting some bit or bit pattern, right? To tell the receiver, okay. So if it is received this 0, then the receiver start to receive some data, right? Now it take the actual data portion. Then again, if the receiver receive this stop bits, at that point it should stop the receive, right? So there are no syncing, right? So sender can sending at kind of a at it can have some intervals, so it can have some like different speeds, right? Sender just sending the stuff, right? So by going through this medium, the receiver can receive at its own method, right? So it can have their own uh, like intervals or something like that, right? So because of we are using this kind of stop bits and start bits to tell the receiver about this actual data portion, right? So about 80% is containing the actual data, because we have to spend some data to tell the receiver about this the transmission, to start the transmission and stop the transmission, right? So we have about 8% actual data on the this mechanism, right? And 20% for the this signaling information, the start and stop bits, right? Right. So the same thing as I said before. So if the receiving end receive this start bits, so it's no the pure data or the actual data will start to flow after that, right? Then again, after receiving the stop bit, at that point, the receiver is know, okay, the transmission is now done, right? So I should wait for another one, right? Then then again, so if you go through this method, right? Stop bit and start bit thing, the asynchronous method, right? So in here, they are using kind of a error checking method called parity bits, right? So parity bits basically means it stores some kind of data or information about this portion of data, right? So it can about the number of ones or number of zeros, like that. It stores some amount of information about this data, right? So if this, while transmitting, the data is changed, right? It can be happen like some kind of interference from the other environment, right? So this data can be changed, right? So at that point, there should be a method to recognize, to identify whether this data is changed or not, right? So this paradigm is basically using to identify whether there is an error or not, right? Not to just, so by using this paradigm, we can't actually recover the data, right? But we can have an idea about whether it has some error with that data, right? So, so this parity bit is stored after the actual data, right? So I'll do example, right? So this is asynchronous, as I said before. That means not synchronizing. So there are no mechanism, timing mechanism or a clock to synchronize both parties, right? So because of that, so the sender and receiver negotiate kind of transmission speeds, okay? Like, so this is transmitter and receiver, okay? Transmitter agree about, okay, I'm sending 100 bits per second, right? The receiver also agreed, okay, I'm also talk with you with 100 bits per second, right? So if these things are changed, so the data will be So the data will be like receiver will receive another data like so. I'll do example. So if so, it's like the in Arduino, right? So you have to when you're using the serial communication, right? So serial means asynchronous, right? That as you remember, right? So in here in serial communication, you have to specify serial begin and kind of a baud rate, right? So if you are connecting another Arduino board, then communicate between these two, right? So you should configure the both baud rates to the same, right? So if it is 9600, both parties should uh, talk with that baud rate, right? So otherwise, so if the baud rates are different, right? So the receiver will send like on the some kind of like that, right? If the receiver receive from 9600, so the receiver will get some kind of gibberish thing, right? So if it is ABC, so if the baud rates are different, right? The receiver will receive some kind of a gibberish content, right? So that's why the both parties have to negotiate for a transmission speed, right? Then you can have gaps, right? Because there are no synchronizing mechanism, right? You just uh, covered your data with start and stop bit and just send in, so you can have your any kind of gaps, right? Okay. Then yeah, suitable because of the gaps and all that, then you have to wait for some period to change the mode, right? So so if this is the receiver, right? So receiver, if receiver receive the start bit, right? Then receiver have to change its mode to the receiving, right? So like that you have to spend some time to switch these modes, and there are some gaps as well, right? Unlike the synchronous method, so the asynchronous transmission basically suitable for low speed, right? So you have to switch these modes and you have to have some kind of gaps to send this data like that, right? So if it is a synchronous one, you have a clock and you can rely on that clock and take the inputs, right? So as a comparison, right? The synchronous basically suitable for fast transmission. The as I said before, asynchronous suitable for slow transmission, right? Synchronous, if it is synchronous, you have to have a clock to synchronize the transmitter and the receiver, right? Right. So if you are giving a clock, say a channel and data line, clock line and the data line, obviously it you have to spend more money on that, right? So you have suppose you have to additionally add this clock line, right? But in the synchronous method, that is there are no clock or anything like that, right? So it's cheap and easy to implement, right? Then also you have to wait until the data can be sent, right? In the synchronous method, but in the synchronous method, you can send whenever the data is ready, right? So you have to just put the start and stop bits and just send the data, right? Then so this is a kind of a comparison, right? So in this communication protocols, we are discussing I2C, SPI, 1 wire, and these are the UART, right? So in today's lecture, we're going to discuss this UART, right? In the next lectures, we can discuss the bus I2C and SPI, right? So so you can have idea after about this table after I done this all this UART and I2C SPI those things, right? Then you can have kind of get some by reading this table, you can get some idea, right? Then, yeah, as I said before, right? So data transmission, there are two methods. No, one is the serial method. Now under serial, we discuss synchronized and asynchronized, right? Now the serial transmission is over, right? We're going to discuss about the parallel transmission, right? So if you have any questions before I move into the parallel transmission, you can ask. Okay. So in parallel transmission, so there's a name called, it's parallel, right? So that means unlike the serial one, so serial means you have to go one by one sequential, right? In parallel transmission, you can send some kind of data by using several channels, right? So you can have several channels like that, right? Then you can send this data at once, right? So multiple, there are multiple channels, and you can send these data bits at the same time to the receiver end, right? So that is the parallel transmission, right? So obviously that is much faster than the serial one because you have the flexibility of the number of channels you have, right? So you can have kind of more channels, right? Like 32 or 64, whatever, right? You can increase the channels and you can increase the speed, obviously, right? Then, so if we are using this parallel transmission, right? So there may be some kind of environment interference on these things, right? So you have to again reconstruct this data packet at the receiver end, right? So so some channels may be slower, then some channels maybe have some issues, right? Like that. So you have to resolve those issues as well, right? So we're not going to discuss those things on this level, right? So if you come into the fourth year, we can look into those things later, right? So almost all the transmissions, transmissions should be synchronized, right? So otherwise the data is not going to receive as we expected, right? As a comparison, right? Obviously the parallel transmission is compared faster, right? The other one is, so we have to about the cost, right? So if you are increasing the number of channels, obviously you are increasing the cost of this transmission, right? And you have to have multiple number of several number of links for the communication, right? Then if it is shared communication, so if you are going to synchronize, only one bit is enough, but in the parallel communication you have to have number of n number of, that means you have three links, you have to have three bits to like synchronize this your transmission, right? Then the crosstalk. So anyone have an idea about what is crosstalk? In the serial communication, it's not present. In the parallel transmission, it's present, right? What is this crosstalk? You know, have idea about that? No?
Overlapping of signals.
Sorry?
Overlapping of signals.
I can actually hear you properly. Okay, crosstalk means, right? So you have several channels, so, right? So you have several channels, right? So crosstalk means, so one channel may affect to another channel, right? So it can be so it can have some effect on the other channels and it can alter the data, right? So So you should avoid the crosstalk, right? So for that, you have some kind of mechanisms to do that in the hardware level, right? So it's like, so we are just sending some voltage levels, no, right? So you know that in the physics things, there are some interference can occur, right? So these, if we are sending some data from on this line, so that will have some kind of effect on the other lines as well, right? So for that, we are in hardware levels, we are using kind of separations, right, to avoid this interference, right? So in the parallel communication, crosstalk is present, right? So also this serial communication is suitable for long distance, right? Parallel communication is suitable for short distance, right? So if you are going to do a parallel transmission on a huge area, right? So that will cost you, right? You have to uh, increase that number of channels, no? Right? So that is the comparison, right? Now we're going to, you know these things, right? So in the A level, so the IT of those things, in the transmission modes, right? uh, Simplex mean there are three: simplex, half duplex, and full duplex, right? Simplex means, so it's like your TV, right? So the TV station broadcast the that whatever the thing you watch, right? So you have your TV, right? Right, you are watching this stuff, right? So it has only one-way communication, right? So you can't, if you are watching a movie or something, right? You can't blame the actors, no, right? So it has only one-way communication, right? So just the TV station just show you the whatever the rubbish you watch, right? You can't take any actions on that, right? So that is the simplex, right? But in the half duplex, it's like your walkie-talkie, right? So you and your friend have two walkie-talkies, right? So you communicate with each other. The police people guys have these walkie-talkies, right? So they are just broadcasting some messages, right? There are some receivers, right? They are just broadcasting the messages, right? After he done the broadcasting, then the another one can reply on that, right? So for at a given time, it has only one transmission, right? So suppose one and two device, right? So one can talk to two and two can talk to one, right? But the same time, those one and two can't speak, right? So well, at a given time, only one can speak, right? So that is the half duplex, right? Then the third one, full duplex. It's like you are talking with your friend, right? So basically, you can speak with your friend, and the same time he can also speak with you, right? So both communications can occur at the same time, right? So he sending some data 1 2 3, and this party also can send some data ABC whatever, right? Like that. So the one is the simplex on a one-way communication, right? Then the half duplex. At a given time, there are only one direction of communication, right? Not that one direction, the direction of the okay, right? So there are only one transmission at the given time, right? Either ways, right? In the full duplex, so all the parties can communicate with each other, right? So these are the mode of transmissions, so if you're not aware, right? Then the good things, the serial communication protocols, right? So if you have any questions, you can ask, right? All right. So in the serial communication protocols, right? In the as we discussed in the parallel interface, right? I said we can increase the number of channels, right? Right. So if you need to transmit 32-bit value, right, in the parallel form of a parallel interface, right? So we need at least 32 pins, right? So the thing is, if you're going to increase this number of channels in your microprocessor, right? So suppose if it is 8 bits, then it's okay, you can have 8-bit channel, right? Then you can transmit that data, right? But if you need to like transmit 32 bit, right? At that point, you can't increase this parallel interface into 32 channels, right? That will you can do, but the thing is, so it costs you some money, right? That's the issue, right? To overcome this, they come up with some mechanism, right? So as I said before, these parallel buses are very fast, obviously, right? So if you're using those parallel buses, you need to have some number of pins, right? So that is the so you have to change the design of the microprocessor, right? And you have to add those pins, and that will increase the cost of the microprocessor and the size of the microprocessor as well, right? So unlike, so they are come up with this method, right? So they didn't go to increase the number of channels, right? So they come up with, so if you need to transmit 32 bits, right? At that point, you can have additional clock cycles. That means, so you have 8 bits, right? So we are transmitting 8, if you have 8 bits, right? We're transmitting 8 bits per second, right? Okay. Then, so if you need to transmit 32 bits, right? At that point, you have to spend some time, the clock cycles, right? Clock cycles and take the inputs, right? So at one pulse, one clock cycle pulse, it gives you 8 bits. Now the second one give you the second part of your data, right? Like that, you can spend some additional clock cycles instead of increasing the number of parallel channels, right? You can spend some time, right? So it may be slower, but it's effective in the sense of the material cost, right? And the physical size of the microprocessor, right? Then, so that will map to the example I had. That's why I put that on the slides, right? So in the serial communication protocols, so these are the protocols we're going to discuss. The first one is UART, right? That means universal synchronous receiver transmitter. Then you have I2C, inter-integrated communication. Then we have SPI, serial peripheral interface, right? So as you can see in this part of the screen, right? There are some designated pins for these communications, right? So most of the time we are using this RX and TX, these 0 and 1 digital pin for the UART communications, right? Then this portion for SPI, and you can do I2C on these things, right? So you can change, right? So you can have a software serial other than the hardware serial, and you can go with these any pins you want, right? So I'll do an example on that, right? So the thing is, there are some pins that are designated for each transmissions, right? So you have to have some idea about that, right? So today's lecture we're going to discuss about UART. Then next day we can discuss I2C and SPI, right? Right. UART basically means universal asynchronous, right? So you know that now what is synchronous and what is asynchronous. So if it is asynchronous, that means what there are. Can anyone tell whether there is a clock line or not? So Why you guys are silent, right? So did anyone tell you to not report? Something like that. Hello?
No clock, sir. Hello, sir.
Okay.
There is no
Yeah.
clock in asynchronous.
Synchronous, okay. Right. No clock share, right. Right. Because this is asynchronous, there are no clock, right? So you have only two pins, right? One is Rx, another one is Tx, right? So the previous here you have Rx and Tx here, right? Right. Yeah, if you're using this UART, right? So these are the Tx and Rx, right? Tx means transmitting, Tx for transmitting, Rx for receiving, right? So if you are using this UART method to communicate between two microprocessors, sorry, microcontrollers, right? So so in that point you have to connect your one Tx to the other part is Rx, right? So the data is shifting from this Tx, right? Ts this pin, right? Suppose data is 0, 1, 1 or whatever, right? So data is shifting from Tx, right? Go to this medium, whatever it can be Y or anything, right? And go receiving to this Rx pin, right? So it receiving it, we basically using the thing called shift registers, right? So I'll get into that later, right? So in a higher level, so basically these voltage levels basically receiving from Tx to Rx, right? Then the other part is Tx. So this is full duplex or half duplex? So one can communicate, Tx can communicate with Rx, right? So transmitter can send, then the receiver can receive, right? Is it full duplex or half duplex? Come on, guys. Right? So, right. So if we consider this whole thing, right? This you have to think like this, right? So if you consider this whole thing, the whole communication thing, right? So if you're not aware about this RxTx things, right? So you just uh, connect these two microcontrollers, right? If you think from this aspect, only thinking about the UART level, right? So not about this RxTx things, right? So this is on full duplex, right? So this can microcontroller M1 can communicate with M2, right? There's a separate channel for that. The M2 can communicate with M1, right? There's a separate channel for that as well, right? So M1 can send whatever he wants, and M2 can send whatever he wants, right? So this is full duplex, right? So if you looking at the lower level and think like that, so that's not going to work, right? So you have to have an idea about the higher level, right? So there are microcontrollers, right? They are connected to each other, right? And at this level, if we watch the communication, so both microcontrollers can talk to each other at the same time, right? Okay, so this is full duplex, right? Then, so if you're going to do this in the practical level, right? So you have two Arduino boards, right? So this TX this TX, this line connected to this RX, right? Then this RX connected to this TX, right? Then this is the most important thing on this figure, right? So you have to ground, we have to make the common ground, right? So that means you are, so this is a separate circuit, right? So you are giving some power and it's work as a separate circuit, and this is also a separate circuit, right? So if you are connecting and if you are communicate with the two in between two circuits, right? So you have to common ground the these both the circuits, right? So otherwise there are some electrical issues, right? So the data will be changed, right? So keep in mind you have to make a common ground, right? Like that. You have to ground the both two, right? Yeah.
Excuse me, sir.
Yeah.
What was the full duplex කියලා කිව්වේ?
මොකද?
Full duplex කියලා කිව්වේ?
Oh.
So එතකොට අර RX TX මාරු කරන්නේ නැහැ මේ අර කියන්නේ දෙක අතර කමියුනිකේට් කරන full duplex නම් RX. එතකොට receiver transmission ඒ wireless ගහන එක මේ software එකෙන් අනිත් පැත්ත හරවන්න පුළුවන්ද?
මොකද?
ඒ කියන්නේ RX TX මේකේ දාන්නේ එකක RX එක අනිත් එකේ TX එකකට දාන්නේ.
ඔව්.
එතකොට ඒක full duplex එක කොහොමද අනිත් එක්කන receive කරන්නේ කොහොමද?
ඔව්. ඒක මෙහෙමයි මම කියන්නේ මේ කමියුනිකේෂන් ඒක තමයි මම කිව්වේ කියන්නේ මේ level එකට යන්න එපා. right? මේ level එකකින් හිතන්න නැතුව අපි මෙහෙම මයික්‍රෝ කන්ට්‍රෝලර්ස් දෙකක් තියෙනවා කියලා හිතලා මේ කමියුනිකේෂන් එක ගැන හිතුවොත් එහෙම එතකොට මේකේ මේ devices දෙකටම මේ කතා කරන්න පුළුවන් දෙන්නටම එකම වෙලාව right වෙන මේ aspect එකේදී මේ communication එක full duplex හරි මේ level එකට දැන් මෙතන අපි RxTX ගැන කතා කරාට ඒක UART වෙන්නේ මේ තුනම set වුණා හරි හරි මේ UART කියන communication එක full duplex හරිද hello
Okay, thank you.
හරිද
හරි sir.
right right then in UART we are basically as I said before we are using something called shift register right so that means it's shifting data in or out right so I'll do example right so it's like suppose you have 1 something like that right so this is the transmitter and this is the receiver right so at each time so suppose this is this part is LSB you know LSB and MSB no? Most significant bit and least significant bit right so this transmission in the shift register that basically shifting this data from if it is TX transmitting one it's shifting out right it's shifting out from this end right? I'll show you example right so it's shifting these bits at each clock cycle so right so you have in your microcontroller you have a clock right at each clock pulse this data is shifting out from this T the transmitting end and the receiver end basically shifting in right it's taking in those data right so I'll show you example right so the shift is starting from LSB you have to keep that in mind right so the LSB is shifting first right so as you can see here right so this is the clock right so by pressing this clock it creating the pulses right by clicking on this thing it can change into 0 or 1 here right so right So if we put some data, right, and creating this, right, so right, I start from the beginning, right? So you have some data here, right? Now each clock cycle, this data is shifting, right? From bit 7 to bit 6, like that. You can insert some data, right? By clicking on this place, right? But in each clock cycle, it's shifting the bits, right? Now, at first, it has it's in the bit 7 and 6. After each clock cycle, it's shifting from bit 7 to bit 0, right? So if we have a receiver on this side, the receiver can take that data, right? Like that. In here, you have some portion of data, right? Then each clock cycle, so this is the shift register, right? You put some data here by clicking on that, you put some data here. Now you creating the clock pulses, right? And these clock pulses, this data is shifting out from this shift register. And so if this is the data out, if you have seen here, right? Now there is a one, now it's shifting, right? Right, like that, shifting and receive from this end, right? The simple idea is this, right? So at this level, we are discussing these things at this, right? So you have a shift registers. You are using shift registers and shifting your data out from transmitting in and shifting into a receiving end, right? This data, you put some data here, right? Now there's one, right? So now there is another one. Now it's creating the clock pulses. These things are shifting like that one, shifting the position, right? You can see it's shifting position and received at the data out, right? And this is another example, right? This will be much better, right? At first, you have some portion of data, right? Give me a second. Right. Right. So at first, you have a transmitter here, and this is the receiver, right? So first you put some data. So you have 0, 1, 1, 1, right? So now the load is 1, right? So you load in this data into a register, right? So if you put this into this place, so the value will look like this. Right? So now it's loaded. Now the transmitting value is 7, right? So in here you have 0. But in each clock cycle, right? So now you are shifting the value, right? Right? Now it's loaded, 0, 1, 1 is loaded, right? Looking at this place, right? You can see the data is receiving. And so the first we have 7 here. After the few clock cycles, you can see the 7 is received, right? So if you put 5, right? So the shift register is creating the pulses and shifting out from TX and shifting in those data to at the RX, right? Initially we have 7, right? By clock cycles, these things shifting out and shifting into RX. And after receiving the whole thing, you have number 70. Then the next example, we have 5 here, right? We creating the pulses, right? After a few cycles, we get in the value we need, right? So that is how the shift registers work, right? So right? In so in UART we have, as I said, we have RX and TX now, right? So both these RX and TX, they have their own shift registers, right? So that's why it's we can identify as a full duplex, right? So we have TX, we have RX, right? So it has TX has its own shift registers. RX has its own, right? So whenever the TX want to send some data, whenever the microcontroller need to send some data, it has a dedicated register, right? He can use that register and shift out the data, right? Send the data, right? So by the time if we need to receive some data from another party, right? So it has a separate register for that as well, right? So by the by the time of sending, it can receive because it has its own register, right? Right. So the both the communication can occur at the same time. At that point, we can tell this UART as identify it as a full duplex, right? Right. Then yeah, RX is basically shifting in the data, right? Taking the data, right? Like taking the inputs, right? TX basically shifting out the data, right? Sending the data, right? As I said before, the can occur at the same time, right? So this is asynchronous, and that because of that there are no common clock shared between both, right? And they should agree with the structure of the data and the speed of the data they sending, right? So it's like the your baud rate, right? And you have to specify the what are the parity bits you put on that data, right? The structure of the data you're sending, right? So you can configure actually in the serial communication in the Arduino you have that serial you can actually you can define that, right? You can define the speed and the parity checks. You can define and you can have your own one, right? But if you are creating your own one, so that should if you are working on 9600, then even parity bits or something like that, right? So so these things should be same for the others as well, right? So other if it is not if you send 10 whatever, so the receiver receive another different one, right? So if the baud rate is higher, right? So it received as a different value, right? That's why if you put some to you can actually try that, right? So even in the if you have a hardware device, you can try, right? So in your serial, you have a serial monitor, right? In the Arduino, you have a serial monitor. In your Arduino code, you can specify the serial begin as 9600 or whatever, right? In the serial monitor, you can have to specify your baud rate, right? So if the baud rates are different, so if you try to print some hello world or whatever, right? So these, if you change this, your serial monitor baud rate into a different one than this 9600, so the values are printed like a gibberish. You can actually read those values, right? So that's why this baud rate should be matched with both parties, right? So otherwise the communication is not going to work, right? It's like talking to a Chinese people, right? We have to this we can do that in the coming years, right? So if you are single and the other one is Chinese, right? You can't communicate, right? So either you have to turn into Chinese, so Chinese have to turn into single, right? So you have to come up with some kind of like a common one, right? So you can speak on English, right? Like that, you have to come up with the common uh, method of communication, right? Common method of settings. These settings should be common for all the parties, right? Then, yeah, data framing. So this thing is these are the theoretical aspects, right? So in theory, right? So these RX and TX, these are some lines, no? Some wires or something. these are at the idle, these are in high. That means, so you have two states, 0 or the lowest stage and high stage, right? I means 1, right? So if there are no data sending from these lines at the idle level, so the lines will look like this, right? So at those are at high level, right? So if the TX want to send some data, right? So you have to, if you need to send some data, right? At that point, you basically taking this TX or the transmitted line to 0 or the low for one cycle of period, like that, right? Now, if the receiver receive this uh, receiver now, if it is idle, so this line should be high, right? So it's known from the receiver end as well, right? If the receiver receive this low line, low voltage, at that point, receiver know, okay, I'm going to receive some data, right? So this is asynchronous. We don't have a clock, right? We have to rely on displays, right? Okay. Now, if the receiver receive this low signal, now we know. Now the receiver know. Okay, now I should change my mode to receive some data, right? So after this start bit or this low one, this low line, this low voltage, right? The data can shift it down. So we know how to shift it down the data, right? So as we discussed the previous slide, right? So at each clock cycle, this data is shifting from transmitting end to and receiving from receiving end, right? Shifting out and shifting in, right? Then, so now the data is shifting out at the defined data rate. That means the baud rate, right? So you have to define whether it's 9,600 or whatever you want, right? So after sending the data can be, if it is 110 whatever, right? So we have 110 like that, right? After sending this data, now the receiver still on the receiving mode, right? So transmitter now done transmitting. After that, transmitter what going to do is transmitter, yeah, transmitter going to. So you can also have a parity bits as well, right? So suppose this is your actual data, right? After the transmitting the actual data, immediately you can send the parity bit, right? So there are methods to do the parity bits. I'll do example, right? So if you are done sending the actual data, after that immediately you can put the parity bits. If the parity bits is 1, you can put 1 here, right? As I said before, we shifting out the LSBs first, right? Then after that, so the data is now okay. Now we have the actual data here. In here we have the actual data, right? Then we have the parity bit. Still the RX at the receiving mode. Now we need to, so the TX now done transmitting the data. Now we need to change the mode of the receiver, right? We need to tell the receiver, okay, you don't need to listen to me. So I'm done sending the data. You can take that data to your buffer, whatever, you can process that data, right? What going TX now going to do is, so we know that at the idle level, so the, as I said before, the idle level, at the idle level, it's in high, right? So now it's going to do that thing, right? So we need to send this stop bit at that point. So we should increase this TX line to high voltage for 1 or 2 cycles, right? So that's the method of the theory behind the UART communication, right? So it has some at the idle level, it's in the lines are at high, right? That means the high voltage, right? To tell the receiver to receive some data. So the TX line low for a one cycle, right? Then you can send the data, right? LSB send first. Then after send the data, immediately you can put your parity bit as well. Then after that, so the communication is now over. Now we need to tell the receiver, okay, I'm done sending the data. For that, the TX line again go for high voltage, right? Okay, so is it clear? So I'm going to give you some some question on the exam, obviously on this, right? So if you can't understand this, please tell me. I'll start from the beginning, right? Is it okay? Is it clear? You just have to have some kind of idea about this, how the things works, right? So TX and RX are high at the idle level. Then if it's sending, it's go for low, right? You can then the receiver identify that TX going from, it's like this, right? So receiver always listening to this portion, the connected line, right? So it's looking at the connected line at some point. So at the idle, it's in high, right? If it is high, that means that line is idle. When that high line is going to low at that point, so this receiver can identify this is as the start bit. Receiver know, okay, I'm going to receive some data, right? This transmission is the key thing, right? So okay, no questions? I was sleeping. So I'll give you a assignment and the exam
Excuse me, sir.
question. Yeah,
Excuse me, sir.
yeah, go ahead.
Sir, then RX ඉඳලා TX වලට transmit කරද්දි, sorry, TX ඉඳලා RX වලට transmit කරද්දි sir මේ අපි හිතමු sir 101 කියන bits තුන transmit කරනවා කියලා.
Oh,
එතකොට මුලින්ම බිංදුව දාන්නත් ඕනේ, at the end 1 දාන්නත් ඕනේ.
101 the
ඒ කියන්නේ 101 transmit කරනවා නම් start bit එක හැටියට මේ බිංදුව දාන්නත් ඕනේ sir.
oh, බින්දුව
at
කියන්නේ
the
බින්දුව
end
දානවා
1
මේ කියන
දාන්නත් ඕනේ. එතකොට 0101 තමයි transmit කරන්න. ඒ කියන්නේ low state එක කියන්නේ අපි 0 transmit කරන්න ඕනේ නේද sir?
මොකද බඩ හරියට ක්ලියර් මොකද කියනක ප්‍රශ්නේ
දැන් data ටික 101 කියමුකෝ sir. data ටික 101 කියමුකෝ sir transmit කරන්නේ. එතකොට දැන් මුලින්ම receiver එකේ high level එකේ නේද sir තියෙන්නේ?
ඔව් high level එකේ
ඒතර low එකට යවන්න අපි බිංදුව කියන bit එක transmit කරන්න ඕනේ නේද?
ඔව් ඒක මෙහෙම
ඒ කියන්නේ low කරන්න.
ඔව් එතන මේක මේ ඒක අපි අතර අපේ පැකට් එක හදද්දී අපි දාන්න ඕනේ නැහැ. මේක hardware level එකේ තියෙනවා. මේ දෙන්න communicate කරන්න මේ level එකේ තමයි. ඒවා already තියෙනවා. අපිට ඒ වගේ low level එකට ගිහිල්ලා එතන ඉඳන් හදන්න ඕනේ නැහැ. අපිට data packet එක අපිට ඒක යවන්න පුළුවන්. යවද්දී වෙන mechanism එක තමයි මේක. හරිද? ඒතකොට data packet එක මෙතෙන්ට වැටෙනවා. හරියටම බැලුවා මෙහෙම තමයි වෙනවා. data ටික තියෙනවා මෙතන. හරි? එතනින් ඊට පස්සේ parity bit එකක් දානවා. parity bit එකේ තියෙනවා. ඒ පැත්තෙන් start bit එක stop bit එක වැටෙනවා. මේවා අපි දාන්න යන්න ඕනේ නැහැ. මේ parity bit එක අපි දාන්න යන්න ඕනේ නැහැ. අපිට direct මේ අපේ data ටික transmit කරන්න පුළුවන්. අපි predefine කරලා තියෙනවා අපි parity bit එක දානවා නම් ඒ දාන්න කොහොමද කියලා. ඒකට මේවා ඒ කට්ටිය implement කරගෙන තියෙනවා. ඒක already implemented. හරි? අපිට data ටික විතර transmit කරන්න
එතකොට sir දැන් data එකේ එතකොට sir data එකේ 1 කියන bit එක තිබ්බොත් මේ square wave එකේ high එකට නේ sir යන්නේ එතකොට එතනට.
ඔව්.
එතකොට මේ කොහොමද දැනගන්නේ මේ හරි කොතනද මේ ට්‍රාන්ස්මිෂන් එක නවත්තන්න කියලා?
දැන් අපි මෙතන ඩිෆයින් කරනවා
රිසීවර් කොහොමද දැනගන්නේ මේ ට්‍රාන්ස්මිෂන් එක කොතනද හරියට නැවත?
ඔව් ඒක වෙන්නේ මෙහෙම. අපි ඩිෆයින් කරනවා අපිට බීට්ස් කීයක් අපි යවනවද කියලා. හරිද? මෙතන අපි බීට්ස් 5යිද 9යිද කියලා අපි ඩිෆයින් කරනවා. හරිද? පැයට බීට්ස් නැත්නම් අපිට බීට්ස් 9 සෙන්ඩ් කරන්න පුළුවන්. හරිද? මේවට මුලදීම ඇග්‍රී වෙනවා අපි. හරිද? එතකොට රිසීවර් දන්නවා මම ගන්න ඕනේ මෙන්න මේ බිට්ස් ගන්න මම කලෙක්ට් කරගන්නවා. හරිද? එතකොට එයා බලන එයාගේ
ඕකේ ඕකේ.
හරිද? එතකොට මේ එයාගේ සයිකල් එක චේන්ජ් වෙන්න පුළුවන් දෙන්නගේ බයිකට තියෙන එක්සැම්පල් එක මම පෙන්නන්නම්. හරිද? එක්සැම්පල් එක දැම්මම හරි. Right. In when you're data framing, you can either go for 5 bits or 9 bits, right? So we can go for 9 bits if you are not using the parity bits, right? So the packet will look like this, right? So you have your portion, you have your data here, right? Then start bit, you have start bit and stop bits, right? It can be the 1 bit or a 2 bit, right? Then if you can have your parity bit here, right? So if you're not using this parity bit, you can go up to 9, right? Then so we consider this example, right? So you have start bit, you have stop bit, and a parity bit, right? So that will look like this, right? So this is 1 0 0 0 1 1 1 and 0, right? So you define the structure of the data, right? So you define the parities and you define the number of bits you're going to send, right? The receiver end just have to fill its registers, right? So yeah, it's basically looking for that number of bits, right? So that's why at the beginning I said the structure should be defined and it should common with all the parties, right? So otherwise, it's suppose you are using even parity on the transmitting end, right? Then the other microcontroller using the odd parity, right? Like that. So if the parities are different and if the speeds are different, at that point the data is different, right? If we send some value like this, the receiver will receive another one if the speeds are different or the parities are different, right? So the structure should be same, right? Then the data rate, the receiver and the transmitter should work on the same data rate, right? So otherwise the data will be the transmitter sending 101 and the receiver will receive 1010 whatever, like that, right? So we tell this we can identify this data rate as baud rate, right? So you already know in the Arduino we have to set your baud rates, right? So yeah, so this baud rate should be saved, and then you have to specify kind of you are using the shift registers, right? So you have to work with the shift registers and you have to like come up with some kind of manageable level of data sending rate, right? So otherwise, so you are using very high baud rate and the shift registers can't work on that. Obviously, that's not going to happen, but like that, you have to think on the both things. So in your levels, so this setting this baud rate is enough, right? Then parity bits. So this parity bit is kind of a important thing as well. It's not very useful, right? So the approach is good. So we basically use parity bits to check, to identify whether there is a corruption on the data, right? So suppose in the transmitting end, you are sending 1101 or something like that, right? Then there are some electrical interference or something, and these values are changed into 10 0, 1, right? Like that. So the receiver is receiving the data, right? Receiver, if we have only this portion of data, right? So the receiver has no clue about whether the data is corrupted or not, right? So the data is whether altered or not, right? For that, they implement the thing called parity bits, right? So that in parity bits, you can store some information about this data, right? Suppose it's like, so if it is even parity, so that basically means you have to count the number of ones, 1, 2, 3. So it should be even parity means the number of ones in your data. This whole thing, the whole data packet should be even, right? So if it is odd parity, so the number of ones in your data packet should be odd, right? So that is the approach, right? So if it is, if you are using even parity, now this work is done by the transmitting end, right? So transmitting end, looking at the data 1101. So there are 3 ones, right? You have to add another one to make this number of ones to even, right? So at that point, transmitter put 1 in the parity bit, right? As a parity bit, right? Now I said there are some interference, right? Now the receiver suppose the parity bit is not changed, right? Now the receiver, no, the transmitter working on even parity, right? That means number of ones in the whole thing, this whole thing should be even. One, other means even, right? Now that the settings are same for the receiver also, right? Receiver know the transmitter sending even parity. Now receiver going to check the number of ones in this data packet. Now there are 1, 2, 3, 3 ones, right? 3 is odd. That means the parity bit is now the parity bit is 1. So the number of ones here are 3. That is not even, right? So that is odd. So at that point, receiver can have idea about, okay, now the data is changed, right? So at that point, receiver can ask for retransmitting, right? So using this parity bit, you can't actually recover the data. You can just identify whether there is a corruption or not, right? But these things are not very useful, right? So these noises we are generating, so it can flip the parity bit as well, right? So if it is 0 at that point, right? Or you can either flip 2 numbers, right? Suppose something like this, right? You are sending some value like 1101, and the other end it's receiving like this, right? So the number of ones are, this should be 1. Right? So these things are not changed, right? But the next 2 bits are flipped, right? So now the 0 goes to 1, 1 goes to 0, right? At that point, you can identify it from the parities, right? So if you are using even parity or parity, so if you are using what parity, right? So the parity bit is 0, right? So you have the number of ones are 3. That means odd. So that's same on the receiver end, but the positions are changed now, right? So that basically means the data is corrupted, right? At that point, these kind of things you can identify from the parity bits, right? For that you can have kind of a high level of error checking mechanisms, right? So, so these things we discussed, right? Okay, so this kind of example, right? So in here, so you can see this is even parity, right? So if it is even parity, now the number of ones we have, so this is the data portion, right? So you have 1, 2, 3, 4. we have 4 ones, right? We have 4s, right? That means you don't need to put another data on the parity bits, right? Because we are using even parity, right? The number of ones are 4, that is even. You don't need to put a value on the parity bits, right? Then this is the odd parity, right? So if you're using odd parity, so you have to count the number of ones, 1, 2, 3, 4. So we have only 4 ones on our data portion. So at that point, make it to odd, we have to add 1 for the as a parity bit, right? Is it clear? The parities and the flipping thing, and that's not a it's good approach on the as a very basic level, but it's not working on the real world, right? So is it clear? Is it okay? Obviously, you're getting exam question on this, right? So you're not talking with me, right? Okay. Then this is the whole picture, right?
Excuse me, sir.
Yeah.
Sir, මෙතන මේ sir මෙතන මේ දැන් bit 1 කියන value එකේ හතරක් තියෙනවනේ sir.
Bit 1 කියන එක මොකද්ද bit 1 මේකද?
දැන් 1 කිය එකේව හතරක් තියෙනවනේ sir. ඒ කියන්නේ එකේව හතරක් තියෙනවනේ. එතකොට even parity නම් ඇයි sir බිඳුව දැම්මේ?
නෑ මෙහෙමයි හරිද?
දැන්
even
යටත්
අපිට
දැන් එකේව හතරක් තියෙන හැබැයි
ඔව් ඉතින් මෙහෙම හරිද? දැන් මේක තමයි අපේ data portion එක. හරිද? මෙතන අපි ගාව තියෙනවා someone asking, so parity is something like validating of the byte transfer. Yeah, it's can kind of give some kind of a validation, some basic level validation on whether the transmitting is interfered or not, right? And මෙතන වෙන්නේ even parity කියන්නේ මෙන්න මේ whole portion එක ගත්තම with the parity bits, the whole portion without the start and stop bit, right? So now number of ones on this whole portion should be even. Even means the mod එක ගත්තා බිඳුවයි කියන එක. හරිද? Then හරිද දැන් අපි අපේ data portion එක තියෙන මෙතෙන්ට වෙනකන් අපි ගණන් කරනවා number of ones 1 2 3 4යි. It's already even, right? 4 කියන්නේ even. හරිද? අපි එතකොට additionally එකක් මෙතෙන්ට දාන්න ඕනේ නැහැ. හරිද? ඒක ඒ data portion එක already even. ඒක නිසා අපි මෙතෙන්ට බිඳුව දාලා යවනවා. හරිද? ඒක තේරුණා?
ඔව් sir.
හරිද? දැන් මෙතන තියෙන odd parity. හරිද? odd parity කියන්නේ number of ones should be odd. right? mod එක ගත්තම එකක් ඉතුරු වෙන්න ඕන. හරිද? මෙතෙන්ට නිකන් අපේ data portion එක තියෙනවා. හරිද? ඔන්න transmitter count කරනවා 1 2 3 4යි. 4යි තියෙන්නේ. මෙතන යවන packet එකේ මේ fully එක ගත්තා මේ ටිකේ වෙන මෙතෙන්ට එනකන් ගත්තාම odd වෙන්න ඕන. හරිද? including the parity bit, right? To make it odd, we have to add another one, right? 1 2 3 4 මේකත් එක 5යි. ඔන්න odd. එතකොට අපි parity bit එක 1යි කියලා දාලා packet එක යවනවා. The directory transmit කරනවා. එතකොට receiver අරගෙන බලනවා හරි parity bit එක 1යි මේ ටික odd parity තමයි මම use කරන්නේ. එයා ගණන් කරලා බලන 1 2 3 4යි. odd එකත් එක්ක මේකත් එක්ක 5යි. odd parity ප්‍රශ්නයක් නැහැ. Number of ones ටික odd. හරිද?
හරි sir. Thank you sir.
Right. So parity is just the basic level of just to tell the two parties whether the transmission is okay or not, right? So if like that, if you flip two numbers, right, at that point it can't identify that error, right? So for that you can go some check some errors or something like that and check the whole thing, right? So this is the overview, right? So So this clock inside your, so this clock not shared with the other party. This is your internal clock, right? So, right. So at first, the transmitting line at the idle level, it's in the high mode, right? Right. You can see it's in high, right? To make a transmission, so the transmitting end pull that high, that TX line to low, right? Pull it to low, right? So if this kind of a transmission, this kind of a transition seen from the receiving end, receiver knows that, okay, I'm going to receive some data, right? Because the idle level, the high channel goes to 0, like that, right? At that point, it's identify that transition and exchange it moves to get some data, right? This is start by detecting the transition from logic 1 high. Logic 1 means high voltage to 0. This transition is identified, then start to receive some data, right? Now we send in the data, right? So we starting from D0 because we are shifting from least significant bit, LSB, right? We are shifting out that data from the transmitting end, right? Then you count the parities and all that. You put the parity bit as well. Now the transmission is over, right? So you can either go for without using the parity bit as well, right? So if you're using the parity bit, that's much good, but it's not 100% okay, right? Then after transmission, the whole thing, then again, the stop bit is sending. That means basically transmitting in that if you receive something at this point, so it pulling the transmitting line and make it into high for 1 or 2 cycles, right? So these are the cycles, right? So you are sending the data from this line, right? So this is your internal clock. At each clock's pulse, you are taking the data, right? So the incoming data is sample with that pulses, right? After receiving the stop bit for 1 or 2 cycles, right? Now the transmitter know, so receiver know, okay, I already received the whole thing, then I should stop listening to the transmission line. Then I go to create the packet and working on that, right? So after, so it basically switching the mode of the receiver, right? Then if this baud rates are different, so this sampling thing will differ, right? So it can either, I'll show you example. Right? So if you're sending some value like this, right? So initially line idle is high voltage. Then to start the transmission, it goes to high to low, right? So that is the start bit. Now then send in the data, right? Then send in the parity bit as well. After that, so the line idle again. So it's pull out and put it into the high voltage for 1 or 2 cycles, right? So what will happen is, so the sample rate, so the baud rate should be same as I said before, right? So this is the sampling one, right? So at each clock pulses, it's getting the information, right? So what will happen if the receiver samples too quickly, if the receiver baud rate is higher, right? At that point, it's skewing to some portion like this, right? So you at the correct as the correct one, you should listen to all this data, but now the rate is high on the receiver end, so that means the distance between 2 clock cycle is very low, right? It's decreasing. At that point, you can see, So these things are, as I said before, they are agreed from whether I should receive the 8 bits or 5 bits or something like that. So it's just creating that clock pulses to take the bits each need, right? So the thing is, if the sample rate is too high at that point, so it will receive the different value, right? So this is, suppose if we label it as 1, 2, 3, 4, 8, right? So this is okay, right? That this header is in first bit. This is also okay, right? So as you can see, that is at this point we can actually tell if it is 6, it's okay. But in here, this clock pulse and this clock pulse taking the same data, right? Because the rate is too high, right? It can't actually. So the same clock at the each clock pulse, it's in here. You can see the getting the same data, right? Now the receiving end receives some different data, right? So as you can see, the last clock pulse also headed to 7, right? So it didn't even looking at the last bit as well, right? So that's why you should come up with some same baud rates, right? Otherwise, it's not going to work. And this is if the receiver sample rate is too slow, right? If it is too slow, that means the time difference between these two clock cycles are increasing, right? It's have now higher value. At that point, these headers are pointing to different values, right? As you can see now, this should be come to this place, right? It should is looking at the portion of this part, right? But because of this sampling rate differences, now it's looking at the different data, right? At that point, it's received some transmitter sending some value like W or something like that, and receiver receiving some dollar sign or whatever, right? Like that's if you, as you can see, this if it has some value like 110 whatever, right? And if we looking at as the perspective receiver from this part, right? You can see these values are now different, right? So you have to set your sample rates or baud rates to same, right? Otherwise, it's not going to work, right? And these are the advantages, right? So you need only 2 wires, right? Then so the structure of the data packet can be you can define, right? Then you don't need to have a clock signals. Then this parity bits basically give you a hard level error detection, right? So if there is an error, then it will triggers retransmitting, right? Then yeah, so these are the disadvantages. Obviously, that is the transfer rate is less, obviously, right? But then the other one is, so the baud rate should be equal, right? You can have a 10% margin on the baud rate, but so it should be almost same, right? So you should maintain the same baud rates, right? But you can have an error up to 10%, right? So then yeah, your data frame is limited to 9 bits, right? So if you are not using the parity bits, you can say 9 bits. And these masters and slaves, I'll discuss those things in the next lecture, right? So there are no masters or slaves. You have only 2 parties, receiver and transmitter, right? So transmitter sends some data and receiver receives some data. Again, so this is full duplex. This receiver can act as a transmitter and this transmitter can act as a receiver, right? So, and that's the end of the lecture slide. So I'll show you some example on the Tinkercad. We have around 15 minutes. right? Can you guys see my screen? Can you guys see my screen?
Yes, sir.
Right. So this is the example of we have two. Here you have we have right now. Here we have two microcontrollers, two Arduinos, right? So it's set up. As you can see, this TX is connected to this RX. This RX connected to this TX, right? So and you should ground the both microcontrollers, right? So now I'm going to send some data from this end to this end, right? So for that, so if you click on this microcontroller, it will show the piece of code inside that Arduino, right? If you click on this, you can see a different one, right? By clicking on this, you can type your code, right? You can have one or more Arduinos, right? So I think, okay, this is the transmitter, right? So first I started as a serial begin, 9600 is my baud rate, right? So I'm going to do a serial communication, right? So as the data, I'm going to send some count from 1 to 99, right? So as a for loop, inside that I'm sending the data as serial dot write and the data. So data is I means count from 0 to 99, right? Then again I give some 100 millisecond delay, right? Then this is not need, right? Then 1 second delay at the end, right? So this is the transmitting end, right? This is the receiving end, right? Receiving end also you have to begin with the 9600 because so the transmitter work on that baud rate, right? Then these things are not needed. Right? Inside this loop, you have to check whether there is a data available on your serial buffer, right? So if there is a data in your buffer, right, then it should read, right? So the keyword is serial dot read. Then you store in some variable called input s and print that value, right? So it. So if we do a simulation. Okay. Right now, both these Arduinos are connected, right? You can see this Arduinos are connected, right? If you see, if you looking on the receiving end, right? You can see it's receiving some value from 1 to 99, right? So it's 99, then the 1 second delay, and it started from 1 to 99, right? So the values are sending from this transmitting end, right? So the values are 1 to 99. These values are sending, and you can receive it from the receiving end, right? So that's how you use the serial communication. Also, you can use software serials as well. You can define your own one, right? So it's like suppose if you're using right, if you're using the hardware serial, right? So you should use this TX and RX 0 and 1 pins, right? So if you need to map for another one, other pins, so for that you can use a library called software serial, right? Then you can define your RX and TX pins, right? Then you can have your own communication, right? Your software serial, right? Call it as my serial, right? You can actually so you can find these codes obviously, right? So the thing is you can either use hardware serial or you can use software serial, right? So the TXRX that switching is you have to do, right? So here in here the RX is 2, in here the RX is 3, right? So you should change it, right? So in here you can connect 2 to 2, 3 to 3, but in your code you can switch it, right? You can define at one line you can define RX as 2, the second one you can define RX as 3, right? You can do the change on the code level, right? And you can the same thing you can only the difference is this, right? You have to specify your RX and TX pins. So RX goes first here, right? So when you're using software serial library, right? So you're creating a my serial, and the first parameter should be RX, the second parameter should be TX, right? Then so the my serial, the baud rate is this, and you are sending some data, receiving some data, and this end you are sending some data, right? So the my serial is the your software serial, your own one, right? My serial dot write the message, the data, right? So the write is for sending and read is for reading and begin for setting up the baud rates, right? So also you can use software serials as well, right? So this is based on the software serial library, right? So with that, I think we can conclude today's lecture, right? So if you have any questions, you can ask, right? We have around 7 minutes, right? Please do your assignments, right? Otherwise you have, so this is a 3 credit subject, right? So we have a kind of a effect in GPA, right? So please working on the assignments, don't copyright, so that's not going to work, right? That's not going to help you on the exams, right? So if you didn't copy and you have lower marks, at least you have to, at least you know you have to try, right? So otherwise you don't know whether you have to try or not, right? Like that. So you have to work on your own, right? You can use the Tinkercad, right? So because of the COVID situation, we can't conduct the physical classes. So for that you can use the Tinkercad, right? In the coming months, if we have a chance, I'll try to conduct at least one session, the physical one. We have time and the environment, right? So otherwise we have to working on the online mode, right? So the people who are copied, they have to, the both parties get zeros, right? So then if you keep doing that, so you have to take some actions as well, right? Okay, with that, you can conclude today's lecture. Thank you.